So this week, I'm mainly gonna present a survey paper that's published in 2020. So last time we talked about transformers, and in the survey there are three categories of models that it covers. So there's RNNs, which already covered, also transformers, and finally the last one is convolutional neural networks. So today, I'm going to compare the three different models, what are their pros and cons, and finally, I'm going to go into more details on the convolutional neural networks. And next week, I will present some simple tricks to improve the accuracy for those models. So some of them might be model dependent, and others might be able to apply to all three models, all three type of models. So we'll first start with some refresh of transformer. So the most important part of the transformer model is this attention module. So one way to think of it is given uh, a bunch of features. So each feature here is represented by a circle. And we want to do a weighted sum of those different features. And the resulting vector can be our input to the next layer. So the way to do that, so the way to get the weights is to um, for the input vector, for each input vector, you're projecting to a query and a key, and you compare how similar the query is to the key by using this dot product. So this will give you um, the weights for the attention. So one way to think of it is for a linear layer, the weights are fixed once you finish training the model. But for attention layers, it's more like a linear layer, but the weights are adjusted dynamically depending on your input. So for every time step, we have this feature vector, and we use linear layers to project it into um, three different types. So the first type is query, and second vector is key, and last vector is value. So you compute the for given so for example, if we want to update the embedding for this particular time step, then we take this feature vector and look at the query and compare the dot product with the keys from the current time step as well as from all the other time steps. And we get a weight based on this dot product. And finally, we take this dot product and do a weighted sum for the corresponding value vectors. So the softmax is how you rebalance the weights so that they sum up to one. Yeah. And this is a detailed formulation of the softmax activation function. So you might input some bunch of random numbers in the input layer, in the output layer, and after the softmax, it will convert it into a list of probabilities so that the sum of the probabilities sum to one. And one such pair of query, key, and value is called one attention head. And you might have several sets of those attention heads. So the idea is that maybe you have multiple sets of attention heads. Maybe each attention head can be focusing on different set of features because all those linear layers are initialized randomly. So that they'll probably converge to different local optimal. And that means it will focus on different set of features. And you can also visualize for each time step which other time steps it's looking at. For example, in the figure on the right, we see that there's a very strong lag of 24 in this attention map. So every time step is looking at the previous 24 time steps go. And a transformer have several of this kind of attention block of the transformer blocks. So inside each transformer block, we have first we have the self-attention, and then we have some sort of residual connection, which is represented by this add and normalize. And then after that, we also have a feed-forward network of two linear layers, and also a residual connection again. So we can stack several of those attention blocks of those transformer blocks to get the transformer model. So each token is very similar to DPAR. We can just represent it as um, the time covariates, the target feature, and as well as the static variables. Okay. Now we can move on to today's topic. So if you're interested to find industry jobs that are related to time series, there are several notable applications. So you can use time series to do climate forecasting. So to maybe to predict what's the chance of precipitation for next week, or what's the temperature going to be like for next week. And there's also demand forecasting or web traffic forecasting, which are very similar. So maybe you think of Amazon, we can kind of use the web traffic to guide as an indicator for how much products likely going to be sold over the course of next week. And there are also applications for in the finance market where you can use time series to do stock trading. And there are some common time series forecasting problems. So there are long-term forecasting, short-term forecasting, which is basically how many steps into the future you want to do the forecast. And besides that, there's also this future of forecasting, which means that maybe for some variables, we only have very limited history. So, for example, on Amazon, maybe we just launch a new product and we have this cold start problem because we don't have a lot of sales history for this particular items. And how do we make the model be able to generalize to this kind of new products? And lastly, in some cases, we care about the confidence intervals. So if we look at the figure at the bottom, maybe the shaded parts are the confidence intervals that are outputted by the model. And this part, we have actually already covered this part, but I'm going to reintroduce all the concepts again using using the notations that are used in the survey paper. So there's a one step ahead forecasting model. So we want to predict one step into the future. So the Y here is our target variable, and the X are all the time-dependent covariates, and the S are time independent. So those are the static variables. And we can also think about this entire time series forecasting problem in the view of an encoder decoder model. So we can first look at second line. So given the past history, the context for the target as well as for time-dependent covariates from the context, we will get this latent variable Z. And based on this Z, we feed into the decoder, which will give us the final predictions. And there are also different type of methods that we can do forecasting. So if we want to predict multiple time steps into the future, one way is to predict all those time steps directly, which is called the direct method. And the iterative method is where we just predict one step at a time and then feed our prediction back into the model to predict the next time step. So that will correspond to the iterative method. And for time series, there are some common building blocks. So there's CNN, which are convolutional neural networks, RNNs, the recurrent neural networks, and also the transformers, which are essentially the attention-based models. So we already covered RNNs and transformers. So this time we'll mainly focus on the CNNs. So convolutions are actually most famous for their applications in computer vision. So given this 2D image, maybe we can apply convolution to extract some of the features. So how it works is that in the top row, we have this 2D image. And for images, most of the time they have three channels. And we look at those three channels independently. So for the first channel, we have a corresponding kernel. And we kind of apply a dot product between the two. So we take the first input channel and first convolutional kernel, and we look at the 3 by 3, the 9 elements in the first input channel at a time. And we do a dot product. So we multiply the corresponding elements and then add them together. And we also do the same thing with the second channel paired with the second kernel, and the third channel paired with third kernel. And then sum the results from the three channels together to get the output for that position. So here, the middle element here is in the second row and the fourth column. Actually, it's the second row and the third column because we only apply here we only show the applying the kernels when the center is one of the elements in the input channel. So here will be the second row and the third column will be the middle element that we apply the filter to. And so we put the just 158 minus 14 plus 653 plus bias to this second row, third column. This will be all the numbers that we have in the output. And so originally, if we just want to keep the original image, maybe our filter can look like the one on the left with just zero everyone, with one in the middle and zero everywhere else. So it only keeps the center element. So this will keep the original image. And if we want to smooth the image, maybe we can just take the average everywhere in the neighboring elements and then put it in the middle element. So this will give us a smooth image. And then we can subtract the two to get the like the residuals, which can be think of as the details of the image. So what I'm trying to get to here is that we can use those convolutions depending on what type of kernels that are learned, we can use it to extract different features from those images. And there are actually some traces where you can define how you want to apply this filter to the image. So in this figure, our filter is this green matrix on the top, and we want to apply it to the blue input channel at the bottom. So dilation means that for each element in the filter, how many elements we should skip every time when we apply it to the input channel. So in this case, the dilation equals 2 because we first apply the first element to the first element in the input channel, and then we skip one element and apply to the third element from input channel, and skip one element again and apply to the fifth element. So in this case, dilation will be equal to 2. And there's also a concept of stride size. So that means whenever so the first time we apply the filter will correspond to this um, blue square here. So we get the first element. And then the second square will be this red square, from which we get the second element. And third element will be coming from this green square. So when we go from blue to red to green, and we move one step at a time, one element at a time, that corresponds to a stride size of 1. And on the right, if we move 2 elements at a time, that will correspond to a stride size of 2. So first we have this blue square here, and then we move 2 elements to the right to get this red square, and then move 2 elements to the right again to get this green square. So if we have this increased stride size, we'll end up getting a smaller feature map at the end. And the last part is how we want to apply the padding. So same will correspond to the idea that after you apply the filter, your output should have the same shape as your input. And all means that even if we only have one element in the input channel, we still want to apply this filter. So we pad a bunch of zeros around it. And valid means that we don't use any of the padded zeros. We just keep all the entries in the input channel must be fully covered by this filter. So if we think about the shape of the output feature map, you'll get a bigger feature map with all, and then valid, and then same, and smallest feature map will be this valid option. So for if we take this convolutional operation into and apply it to a neural network, apply it to a CNN, maybe we can first have one layer of convolution, and then we do some pooling. Pooling means that maybe we take the maximum elements out of every 2 elements, or we take the average out of every 2 elements. And then we can apply a convolution again, and then pooling again. And we iterate this process several times to get a final feature map, which is 2D, and can flatten it out into a 1D vector, and then apply a few linear layers or some kind of fully connected layer at the end to get our final prediction. So this is how it works for images, but we can also apply the same concept to time series. And in the case of time series, maybe instead of having just 2D convolution, we have a simple 1D convolution. So the input channel here will be this green vector, and our filter will be this yellow vector. And when we apply this yellow filter to the green vector, we'll first multiply the zeros, the first element from the filter to the fourth element. Or actually, in the equation at the bottom, I wrote it the other way around. So the x0 will multiply with W4, and then x1 multiply with W3, x2 with W2, etc. And we add them together to get the output for that corresponding position. And a very popular architecture in the case of 1D convolution is this wavenet architecture. So the idea of a wavenet is that we want to use as few layers as possible, but we also, at the same time, we also want to look at as many time steps as possible. So we do that by just looking at each input time step one time, exactly one time at any layers, and at any of the layers. So if we look at this last node here, each of the input time step is attended to exactly once. And the way we do that is by having this exponentially increasing dilation factor. So in the first layer, we apply a dilation of 1. So what that means is that we just look at each time step. And then in the second layer, we increase it to a dilation of 2, which means that we skip one time step at a time from the previous layer. So we first look at the first element, then the third element, and then the second node here, it's dashed, but if you look at this dash arrows, it's looking at the second element and then fourth element, and so on. And then we do the same thing with the third layer, which has a dilation of 4. So that essentially, as we go up the layers, each time step in the input is still attended exactly once every time. And there's also this concept of causal convolution, means that because we cannot look into the future for time series, we must look into the past. So this causal convolution means that we only apply it to the previous time steps. So here's some summary on the convolutional neural networks. For convolutions, we actually use the same the same filter across all the input time steps. So for example, if we look at this first layer here, the two arrows that we're merging, we'll use the same weight for the first two arrows, and then the third and fourth arrow, and then the fifth and sixth arrow, and so on. So essentially, we are applying the same filter weights to every time step. And another maybe a disadvantage of convolutional neural networks is that your how much time steps that your model can look at is limited by this receptive field. For example, in this figure, if we are at the fourth layer, maybe you can only attend up to the first node here. We cannot look further back, or otherwise we must have more layers in our neural network. And compared to RNNs or transformers, because we are applying this filter with the same weights, it's actually better at capturing those local patterns. So if we want to just have some specific patterns that we want to look at, maybe there's one corresponding um, filter that we can apply. And we can just apply that filter to all the time steps without having to learn it for each of the time steps. So this kind of local pattern is also known as shapelets. And for RNs, we can look back as many time steps as we want to. So potentially we can support an infinite length context window. But the disadvantage of RNNs is that we must force everything into a fixed size memory vector. And the memory vector also need to be updated recursively. So if we want to train a very large network, maybe that will be very slow. And for transformers, compared to RNNs, we don't have this fixed size memory vector. We can just look back an arbitrary number of time steps ago and just compare their dot products if we want to pay attention to that particular time step. And not having this memory vectors that need to be updated recursively allow us to make the training process as well as the inference process a lot more scalable. So it'll be much faster to compute. But there's also this quadratic memory requirement. And if the vanilla transformer also treats each time step as a separate token, so it kind of loses the connection from the current time step to the neighboring time steps. And in next week, we'll talk about some tricks to deal with the last issue here. And this is summary of the three type of networks. So we have transformers, the CNNs, as well as the RNNs. Okay, this is actually what I have for today. So we mainly just talk about convolutional neural networks, and then we compared its pros and cons to RNNs and transformers. Um, So if we look at the model performance, actually CNNs are um, most of the time a lot better than RNNs and transformers when it comes to classification. So if we have different time series and we want to classify which one belongs to a certain class and which one belongs to a different class, because for those classification tasks, it's oftentimes it's the local shapelets that we care about. And if we want to do forecasting, um, transformers and RNs are very good at doing this, predicting to the future if we don't care too much about the local shiplets.